and welcome back to the Ocean Stage at North Shipping 2023. Please join me in welcoming our next guest, Angus Whiston of DeepSea AI. Angus, the stage is yours.
Thank you. Good afternoon, everybody, for 31 seconds. It's great to be here. I am going to tell you about 3 things. Firstly, we're going to talk about certainly what we believe is the most foundational, fundamental problem with vessel efficiency today. We're then going to talk about the one, and there really is one way of fixing that problem. And thirdly, that will naturally lead on to an understanding that we're already seeing about how rapidly, as this technology is advancing, there will come to be 2 classes of shipping companies. One that has an AI foundation and reaps the benefits almost immediately, and the others that fall behind. And very quickly, that will lead to, as you can see, the topic of my talk, which is how this is not an optional choice anymore. So I don't think I need to tell you, I'm sure after 3 days here and years in the industry, you are all aware of the challenges facing shipping. So I won't go into that. Instead, I will ask you to imagine with me. You are an operations manager, as perhaps some of you are, in a shipping company. And your wife, or husband, or boyfriend, or girlfriend, or whoever is also an operations manager in another shipping company. Let's call it Company X. And you come home at night after a long day in the office, and you get into bed, and you put your head on the pillow, and you turn and you say those most romantic words. You whisper, "What was your quarterly TCE?" And you hear the answer. And again, for the 3rd or 4th quarter in the row, it's higher than yours. And this is important to you because you run exactly the same kind of vessels. In fact, you run exactly the same ETAs, the same routes, the same trade. In fact, it's an identical model. And so you turn over on your pillow and you say, what is happening here? They're doing everything the same. And yet, consistently, time and time and time and time again, they're beating me. And it leads you to conclude they have an unfair advantage of some sort. Now, of course, it's not an unfair advantage. There is just one thing that they are doing differently, which is they are getting everything right. What do I mean by that? They leave port. Company X's vessel, your competition, leaves port. Currents from astern, winds from 33 degrees, both of a certain magnitude. And they make the precise change to their speed or route to minimize fuel consumption across the entire voyage. 4 hours later, those conditions have changed. And again, they have made the precise, exact, correct change to minimize fuel consumption across the whole route. And then again, every single time. And this success compounds. The first time, hey, they save a ton. The second time, they get it right again, they save another ton. The third time, they get it right again, they save another ton. And then you're turned over on your pillow and you're thinking about how this works in your organization. You leave port. OK, we'll go the same speed. Conditions change. OK, we'll make a change. We know what to do in these conditions. You save a ton. 10 hours later, the conditions become a bit unusual. You make the wrong move. You wipe out the ton that you saved. And in fact, you lose another ton. And this goes on and on and on. Are any of you chess players? Great. Magnus Carlsen, who is a famous chess player for those of you who don't know, he said something which I thought resounded quite a lot with this. He said, throughout a normal game, he knows the moves to make. But there comes a point, maybe 1, maybe 2 points, where he can see all of the possible options. And at that point, if someone could just give him a hint, the right answer, he would be unstoppable. Always. He would win. Just the one right answer. And if you get the wrong answer, like I do most of the time, you can end up losing. The truth is, and I know this may sound controversial, but we really don't know, as an industry, how vessels behave. OK, a good captain with a good crew, backed by a good operations team, knows very well, let's say 85% well, let's say 90% well. Just think back to that first slide. Think back to the challenges. Think back to the CII challenges. Think back to the EU ETS challenges coming up. Think back to the fuel price. Think back to the commercial challenges. And think back to the shareholder pressure and the commercial pressure that is increasingly being heaped upon all of us. A 90% accuracy, shall we say. What could we do with that extra 10% if we knew what it meant? What does that 10% inaccuracy, uncertainty, mean for your CII next year? Quite a lot. But I didn't want my word to be the final point on this. I went and did a survey across the industry, all vessel types, all trade types. In fact, some of you, I expect, may have answered this survey, in which case, thank you. I asked, how well do we as an industry, you as operators, how well do you understand the performance of your vessel in good weather? The answer was, quite well. Quite well. And on one hand, quite well is quite good. It's great. But on the other hand, is it enough to say that in the next 3 hours, we will have 1.5 knots current from 43 degrees, plus wind of this magnitude at this angle, plus this draft and this swell and these waves? Is it enough with those conditions to be able to say this is how fast you should go? Of course it's not. That's in good weather. In bad weather, still, most people know quite well how their vessels behave. We're starting to get now into a little, though, and that's where my kind of chess playing comes in, right? Where you can see the clock is counting down, and you randomly make a sort of chess move, a sort of pawn move on the left, and hope that the opposition hasn't seen that you've just opened yourself up to checkmate. But at the end of the day, where is this knowledge enshrined? There's always a model, whether it's in the head of the captain or the operator, or whether it is on paper in a digital format. It turns out that this understanding that we have as an industry is largely fixed in generic models. For those of you who don't have a familiarity with this, just briefly, a generic model of a vessel is sort of what it sounds like. So you have, for a particular vessel class, let's say a VLCC, you have a model which can have a number of different types. It can seem like a number of different things. It can be a fuel table with a few different speeds and maybe 2 or 3 different weather conditions, and then how much fuel you'll burn per hour, per day, per minute. Or it could be something a bit more advanced. Regardless, it is for a vessel type. And I think we're probably, at this point, all tired of repeating that old maxim, no 2 vessels are the same. Even 2 sister ships are different in blah, 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 right? We all know that now. And we know that those differences can be significant. especially when we factor in that generic models almost never include fouling. And yet fouling is, especially for a technical department or for an operations department, one of the biggest problems and the biggest ways of improving or hindering the efficiency of your vessel. A generic model can be many things. What you see before you here is a visualization of a type of generic model. In fact, it's quite a generous rendition of a generic model. What we have done here, in order to create this for visibility, is we have taken one of our very high frequency, very high resolution, very granular vessel behavior models. We have made an amalgam across all of the different ships in our database of a similar type. And we have then, for anyone who's technical in the audience, we have quantized the power dimension so that it starts to resemble effectively a fuel table. Although in this case, you can see there is an awful lot of granularity on the angle and the speed of the wind. What you see before you is a model which shows how much power is going to be required for what wind speed and what wind angle under a particular vessel speed, and all of the other dimensions the same. And this is good. Again, just as the industry says, we understand our ships quite well. This is quite good. But is it enough to get from 90% to 98% accuracy, or as high as you can get, in order to take advantage of that 10%? What is that 10%? What does it mean? Let's talk briefly a bit more about this generic model and these generic models that are the industry standard at the moment. For those of you out there who are working with ETAs, so your liners or semi-liners or whatever, then what does it mean? This is the only graph I'm going to show you. At the top, you can see a simplified current plot across a particular voyage. Now, this is a real voyage from last year, which we've simplified here to make it easier to see. But this comes directly from a plot that we saw. You can see that in the first section, there is a pretty significant adverse current, which then, in the middle of the voyage, becomes consistent, no current. And then towards the end of the voyage, the current becomes favorable, slightly. Now, I want you to look at the purple line. Directly below the current plot, you can see the speed of the vessel. And the purple line indicates what the generic model suggests. It suggests going slower with the adverse currents. It then suggests a fairly consistent speed and a speed up towards the end with the favorable currents. And then if you look at the white line, that is what is optimal. Now, in many ways, this looks pretty good. The generic model trends in the right direction. Great. Again, quite good. Quite good. It's getting there, right? Looks reasonable. But actually then, we come to our old friend, which is the wonderful cubic relationship between speed and power required, and therefore fuel consumption. And what this means is that actually that over-adjustment on both sides of this equation that the generic model said that we should follow leads to a vastly disproportionate fuel consumption. And in fact, the fuel that it saved versus the optional in the first bit of the voyage is totally wiped out in the last bit of the voyage. And this is what I mean. We're getting there, but you have to get everything right, or you could end up in a worse position. This voyage, by the way, this issue was worth $12,000 on this voyage. For those of you who aren't working with ETAs, but are working with TCEs as your objective, then we all know that the most important thing you need for a TCE optimization is an understanding of how your fuel consumption is going to vary with the duration of your voyage. In truth, I've actually never seen one of these graphs genuinely generated by a generic model. I'm not sure that they exist for various reasons. But what you are left with is something like this, right? It's a theoretical curve that follows understood laws and says, well, this is the fuel consumption that you will have, nice and consistent, taking into account, of course, the fuel consumption roughly of your vessel. That's what you're working with, right? Where's the weather? Is the weather an issue in shipping? We believe so. We're an AI company at DeepSea. We have been working on this specific, precise problem for 6 years now. And it really comes down to one thing. How do we boost the understanding of those vessels so that we can help you to get everything right, so that you can make the right chess move at the right time and have exactly the opposite answer than what you would have had before? You win. You win. Your TCE is better consistently, foundationally, across the board. It's a systemic thing that you can get right time and time again. How the hell do we do this? We're in an age now of AI. And I'm going to tell you now, for the first time, how this actually works. Because we know that this AI can come, it can take over our ships, it can steal our jobs, it can become sentient, it can decide it wants to be a ballet dancer, it can do all sorts of scary things. So here we go, guys. At the end of the day, this AI tells us one number. One number. All right, actually a few numbers, but ultimately at the end of the day, the one number is the one we're looking for here. What are the conditions? So going back to that story, you've got company X and your own vessels. Every step of the way, they're making the right decision, the right tweak to the route, the right tweak to their speed policy. And it comes from a calculation. You say, what's the wind? What's the wind angle? What's the currents? What's the current angle? What's the swell height, the swell period, the wave height, the wave period, the salinity, fouling state, precisely, very, very important for currents, as you can imagine. Speed over ground, draft, and loads more. That is what you need to put into the equation. What you need to get out is, if you travel at X speed, what's the fuel consumption going to be per minute, precisely? And once you know that, the rest becomes quite simple. And of course, there are challenges and limitations, such as weather forecasts and all that lot. But fundamentally, this is it, guys. This is what we need to know. This is a high-definition revolution in shipping, and it needs to happen. Until now, working with generic models based on noon reports, if we're lucky, with one reading a day for a few manually entered metrics. We're in low definition. We're in YouTube 2006. It's grainy. It gets us there, but it's not comfortable. And in today's world, it's not right. Without question, the future is about high-frequency data coming from ships regularly. It happens in cars, happens in all sorts of other industries. And now, very rapidly, we're delighted to say that this is happening in shipping, as we all know. With this high-frequency, high-resolution data, we build high-resolution models. As you can see here, this is one of the models that we have built. It's a simple visualization where we've fixed all of those parameters that we've just talked about, those factors. And what we're just visualizing here is the power required and the fuel consumption that comes from it, with different wind speeds and different angle of wind. Everything else is the same. This is for a particular speed through water. So how does the reality look when we throw away those generic models and throw away that 10%, if we're being generous, inaccuracy, uncertainty, black hole? If we fill that, what does it mean? Well, we'll go back to this. That optimal line that I showed you is actually the custom model line. These models that we build, and what is an integral, foundational part of taking that 10% and making it yours, is custom vessel modeling. Every vessel is different. You have to model each vessel, each specific fouling state, the engine, the pistons, all of that plays a part, right? And so this gives you the custom model. Here, what it has shown is that, yes, what the generic model said is roughly right. If you don't get it all right, you wipe out all the success. What it's done here is the custom model knows precisely how your specific vessel is going to respond to those specific, probably unique set of conditions. And you can see it suggests, for this vessel, a less extreme change. It doesn't overreact. It doesn't have to overcorrect at the end. And that leads, in this instance, to a much more consistent speed. And again, thanks to thanks to avoiding our friend the qubit relationship, then let's save $12,000. This is fun. So for those of you, again, who are working with TCEs, have a look at this. This is still radically simplified, but this is what you need, right? We are looking at how the duration of the voyage impacts the fuel consumption with weather included, which is the reality. And so you can see here that actually that storm, for example, or whatever it happens to be, will make a vast difference to your TCE optimization. It allows you to work out the marginal cost curve, which allows you, at the end of the day, to find the equilibrium point between the duration, fuel consumption, and the TCE opportunity at the end of the day. Whether you are optimizing for fuel with an ETA or whether you are optimizing for TCE, you all know this is marginal. Let's say 5%. What does that mean in terms of CII? What does that mean on your annual fuel bill? Quite a lot. But does it make an actual impact at the end of the day? This has been nice theory. Makes sense, I hope. I see a lot of you nodding along. So I asked the most impartial source I could find on AI, does AI make a difference? And the smug bastard said, yeah, sure it does. Yeah. Over the last 3 months, we have run what I think, correct me if I'm wrong afterwards, I'd love to see the studies, but I'm pretty sure this is the first genuine scientific study on the impact of the status quo in the industry, generic models, versus a well-executed custom model. And actually, to be fair, it is what we've chosen here is quite a well-executed generic model as well. How did we do this? We took 3 vessels of different types to give a good cross-section. We took 25 real historic voyages. We have the fuel consumption. We have all the data from these vessels and these voyages, which gives quite a big sample size. For exactly the same route and exactly the same algorithms consistently across this experiment, we used the generic model to optimize just the speeds. Just the speeds. The route is exactly the same. And we saw what the difference in fuel consumption would be. Then, as part of this simulation, we did exactly the same, identical, but we removed that inaccurate generic model, and we supplanted it with a custom model with 98% accuracy, which is what we're typically seeing. Between the real historic voyage and the speeds optimized with the generic model, we saw a 2% difference. Now, this can be taken with a pinch of salt because we're not fully sure how the voyage previously was sailed. We know it wasn't with a generic model. We know it wasn't with a custom model. But there's a lot of randomness in there. So this is the baseline. This is the interesting one. Given that we have established that baseline, we can say scientifically that for these vessels, at least, the difference between using a generic model and a vessel-specific model, with everything else kept the same, was a 6% difference in fuel consumption. Getting everything right yields a 6% improvement to fuel consumption. Why? From where? How exactly? Moving from the standard definition version of reality to the high definition version of reality, the voyages were tailored to the true weather impact, as we've talked about. They also avoided these common things in the industry like safety buffers, because you know you have to get to the ETA, for example, but you're not quite sure what the weather's going to do to your vessel in the last quarter of the voyage there. So you leave a big safety buffer, you go faster at the beginning, you slow down towards the end. Well, we know now. We know what that means. And so you can factor the weather in correctly, efficiently. And finally, just one point on this. The constant power approach is becoming very common in shipping. It's a great approach. It makes sense. Some people have asked us whether this is an alternative to that. Of course, it's not. These models encapsulate that as a perfectly reasonable possibility. Where the conditions suggest that is the right thing to do, that's what you get. Where it's not, you might get something quite different. Vessel-specific, condition-specific, always genuinely, truly, for the first time, optimal. Let's just round off by putting a value on these models. At the end of the day, what does this mean, this revolution? Well, let's take a ship burning 40 tons a day. With that 2% improvement with this nice generic model, this model is worth to you $500 a day. That's what it's saving you by moving from a more experiential-based or weather routing approach to a generic model-based approach. $500 a day. Nice. Great. If that model saves you $500 a day, this model saves you $2,000 per day, per vessel. Plus, what we've seen typically is at least one CII. But, of course, for every vessel and every shipping company, for you, it's always different. For Wallenius Wilhelmsen, this model was worth $2,031 per vessel per day. Because you've got to check it out in reality, see how it functions in your organization, along with the platforms that it goes with, along with the human adoption and how that progresses. It was quite nice, this, because doing all that theoretical research, which came long after we started working with these guys, it was very nice to see how these numbers come together. And you can go and download this case study, by the way. The results of this experiment, which we think are pretty important and actually confirm the things that we all already know, we're going to be publishing in a white paper in the coming weeks. But in the meantime, for anyone who is interested in understanding how this will work in your organization, do jump onto this QR code, book a lightning session with us. We can tell you about your specific use case, how it will work for you. And at the end of the day, guys, I hope now, coming right back to what I was saying at the beginning, this is a systemic change, one that actually costs comparatively little compared to the amazing impact it makes on every voyage. And you can see how, as the shipping companies that are adopting this become more and more, the the competitive landscape starts to shift. And it is our firm belief, because it seems to us a no-brainer, that in the coming years, certainly within a decade, you either have to adopt this kind of technology as your operating norm, or you will not be able to compete. Thank you very much. Great to see you all.